Thank you, Laurie, for inviting me to speak tonight. It's great to see a lot of familiar faces I haven't seen since before 3 years ago, so thanks for inviting me. So I'm going to speak today about my home retrofit project that I've been working on for the past 15 years. As Laurie mentioned, my day job, I'm working in mechanical engineering, and I do energy simulation, mechanical systems design, and today I'm going to talk to you about what I've been doing in the evenings and the weekends. So a little bit of an outline here. So I'll start off by talking about my home, a little bit about the pre-retrofit energy use, and then I've kind of broken up the renovations into two phases. So the first phase was related to the building envelope. I added some energy monitoring after that, and then within phase two I looked at the mechanical systems, and then I replaced some of the appliances. So the house is in Halifax, just across the harbour. 115 meters squared is the floor area, 1.5 stories. And the building permit from the home is from 1915. I was able to find that at the public archives, so I did a little bit of research that was interesting. The actual owner, who happened to be the builder as well, ended up dying on December 6th, 1917. I don't know if anybody might be, yeah, that's it, the Halifax explosion. So unfortunately, he died in the Halifax explosion. He was a master carpenter that worked at the Halifax sugar refinery right on the harbour. So then he unfortunately died that day, and then his body wasn't found for about 4 or 5 months afterwards because of all the rubble and everything. But I saw that his wife ended up living in the home for another 20 years or so. But I think he did a pretty good job of building the home for that point in time. So a little bit about design conditions in Halifax. As a lot of people here will be familiar, we design for about minus 16 Celsius and about 4,000 heating degree days, 26 degrees Celsius dry bulb in the summer. Indoors, 22 degrees Celsius is what we normally keep the home at, although I vary the temperature a little bit based on the season, based on comfort, so maybe 21 degrees Celsius in the shoulder seasons, and 22 degrees in the coldest parts of the winter. Started off with 2 occupants in the home, and now we have 4. So here you can see the mechanical systems in the home whenever I purchased it. It was used oil-based heating system. So we had an oil warm air furnace and oil-fired water heater. The above-ground walls were uninsulated, so we had empty stud cavities, and there was R2, 1/2 inch of EPS insulation on the outside of the walls. So that was bad for the previous owners, but it was very convenient for me, where it was easy to add insulation. A little bit of insulation in the attic, and the windows were mostly old, the original windows, I think, to the home. So as you can see here, the greenhouse gas emissions were around 15 tons. So I had asked for the energy bills from the previous owner whenever we purchased the home, and they were up around 15 tons of greenhouse gas emissions, split about equally between electricity and furnace oil. And the energy use was around 125 to 150 gigajoules a year. So what we did the first day I think we moved into the home was we got an EnerGuide energy audit. We ended up with an EnerGuide 34. So this is with the older system, which would mean 100 would be net zero, 80 would be like an energy efficient new home, 34 would be a very inefficient home. So we were at 17 air changes per hour, which probably isn't that unusual for a home that has no insulation in the walls. I calculated the Teddy, and we're probably up around 230 kilowatt hours per meter squared, so that's about 10 times like what a passive house would have for heating demands. So that year, actually, we rather than taking the approach that a lot of people take in, like pretty up the home with like new siding or new paint or anything. We actually spent the first year doing energy efficiency retrofits. So thanks to my wife to letting us focus in on that. So we blew insulation into the walls, and we added rigid insulation into the basement, added some insulation up into the attic, and then replaced a few of the appliances. Soon after, within the first couple of years, I added some energy monitoring. So I added an energy monitoring system, and that's able to monitor temperatures and status of equipment. I added a flow meter, and then you're able to build like a website. And I was able to, I added a solar domestic hot water system, and I monitored the performance of the solar system basically with that. And that was the first thing that I did. So this was a little bit of an example of the graphs that you're able to produce with the monitoring system. So I would log in and check in on this, and sometimes I would call home to my wife and be like, "Oh, I saw you took a shower this morning," or I could see like the whether or not the temperature of the tank was dropping or anything like that. So I was kind of checking in on that once in a while. One thing you can see here is this red line that goes left to right. This is a 24-hour period. This red line is the solar tank, or actually the glycol loop that runs up to the solar panels. So you can see that the tank temperature, or the loop temperature, was cycling up and down quite rapidly in the afternoon, and that was because the system had peaked in temperature. So this was even in April of my first year. So we had oversized the system really, so it was able to fully heat all our domestic hot water in April, and then the system was kind of cycling on and off. This was its first year of use. In the yellow bars is the solar fraction, so anywhere from 15% of our domestic hot water use that we do in the winter up to 100% in the summer. And then the blue bars are the domestic hot water use in liters per day. So we're averaged around 90 liters per day of domestic hot water. So we actually were able to, we shut off our supplemental domestic hot water source and just ran on solar usually for the summertime. So this gives the results after the first 5 years. We were able to save 50% on energy use, 50% on greenhouse gas emissions, and most of that is due to the envelope retrofit. So I look back at the numbers. I think we spent $5,500 on the envelope upgrades, and we got an incentive of $3,500 from the government. So the net difference was $2,000, and back then in 2008, 2009, the price of oil was sky high. It was actually, I think, $1.40 a liter for furnace oil when we purchased the home. So I had less than a 1-year payback to upgrade all the building envelopes. So it made a lot of sense to do that. So it kind of made me think, like, why isn't everybody just doing this? It's like less than a 1-year payback, and you can reduce your energy use by 50%. And that continues on through the life of the home. So we cut the air leakage almost by half, down to 9 air changes, and the energy demands, the Teddy, I think, went down to about 90. So still 3 times passive house, but it's still pretty good. So the next part was the part that I was really looking forward to, was selecting the heating system, new heating system. So I created a spreadsheet, of course, looked at different heating system options. Now this spreadsheet goes from top to bottom with the highest greenhouse gas intensity to the lowest greenhouse gas intensity. So I looked at electric heat, and back in 2011, Nova Scotia Power was about 752 grams per kilowatt hour of carbon. And then I looked at air source heat pumps, ground source heat pumps, furnace oil, and natural gas. And at the time, natural gas would have been the cleanest, greenest option. And I also looked at, well, what about over the next 15 years if the equipment lasts for 15 years? So I assumed that the grid may get 3% cleaner a year over the next 15 years. Didn't quite work out that way, but all of a sudden, ground source heat pump would be the cleanest. It would have jumped ahead of air source natural gas. The air source heat pump was the next best. So What I ended up choosing, though, I looked at natural gas, but it wasn't available on my street, and I'm kind of happy that I ended up choosing air source heat pump in the end. So looking more into the future, so I ended up choosing a two-stage heat pump. There wasn't any variable speed compressor heat pumps available really in 2011. So I just chose the most efficient two-stage heat pump I could get. This is a little bit of a graph just showing the different options that I looked at. I looked at if I hadn't done the building envelope upgrade, what size of heat pump would I need, as well as with the building envelope upgrade, what size of heat pump. So the orange line here is the heating load based on the outside air temperature, which is on the bottom x-axis. And the blue is with the envelope upgrade, what the heat load would be. So it's more than cut in half with my envelope upgrade I'd done a couple years before. So I would have needed a 5-ton air source heat pump if I didn't do anything, but instead I just needed a 2-ton. And on the far right, you'll see the cooling load. And my cooling load was about 1.5 tons. So it wouldn't really make sense to put in a 5-ton air source heat pump for heating and then have it so much oversized for cooling. So the upgrades ended up really making a lot of sense, saved a lot of money on the heat pump, and also, I didn't have to replace the ductwork, and so there was a lot of benefits there. A little bit on performance here. All I want to point out here is the red line again here. So the red line is my supply air temperature from the heat pump. It's about 30 degrees Celsius. But you can see that it starts getting really jagged at one point in time. Whenever it gets a little bit colder outside, that means the supplemental heat is starting to kick in. So if you look at the blue line across the bottom, it's just below -10 or right around -10. That's the outside air temperature. So if you might remember on the previous slide, my balance point temperature is what the dashed vertical line is. It was designed it for about 30 degrees Fahrenheit or about -1 Celsius for the balance point. In reality, the supplemental heat didn't kick in. It doesn't kick in until about -10 or -11 Celsius. But in reality, that was overnight. The sun comes up and the sun comes out in the daytime, and you can see there was like a 6 or 7 hour stretch there where it didn't have any supplemental heat down at -10 or 11 there. So you can also see there's defrost kicking in every 6 hours. So it doesn't kick in very often, so it doesn't really have a big impact at those temperatures. So that was 2011. So work got busy, added 2 members to our household. So I didn't get a whole lot done for about another 9 years, till 2020. So 2020 hit, all of a sudden I had a lot more time at home, a lot more time to spend around researching different equipment. So I looked at heat pump clothes dryer and heat pump water heater, and I wanted to add ventilation into my home, so I added an ERV. Just did a little bit of monitoring on the heat pump clothes dryer. As you can see in the orange, this is the energy use of the heat pump clothes dryer. So you can see here that over about a 3-hour period, it takes about 3 hours or more to dry our clothes. It only uses 800 watts, which is nice, compared to typical clothes dryer will use about 5,000 watts, might run for an hour, so about 5 kilowatt hours. This uses 800 watts for 3 hours, about 2.5 kilowatt hours, so saving 50% on your energy use, but it takes a lot longer to dry. I realized I kind of made a mistake in selecting the dryer though, because it's selected to be the same volume as my washer, which was a mistake. You want to have your dryer as about twice the volume as your washer. So we end up overloading the dryer too, which causes it to run longer. But we still see about 50% savings on the dryer energy use. I have a meter that meters the heat pump clothes dryer too. The heat pump water heater that we put in, it actually replaces the solar domestic water heater. We were getting our roof redone, and I just figured maybe it's a good time to go and try new technology for domestic hot water, so I went with the heat pump water heater. It runs for about 4 hours, 3 or 4 hours in the morning, and then again in the evening. It's not really a big problem though, because the temperature in the tank still stays warm. But one thing I noticed is The energy used for the heat pump water heater is about the same or less than what we used to use whenever we had the solar domestic water heater, because there was the supplemental heat that we needed to run that whenever it wasn't sunny, like especially in the wintertime. So we end up using maybe less energy, but then it does use heat out of the home. So it's just inside my basement, so it sucks heat out of the basement to heat up your hot water. And so that makes my heating system work a little bit harder, but in reality I just have a little bit cooler basement, but that's not so bad. I did a few measurements on the sound level. From that, it does generate a little bit of noise. My model is pretty quiet, it wasn't too bad, but I have my workbench that's right beside the heat pump water heater. It was blowing a lot of air right at my workbench whenever I tried to work at it, so I put an elbow on the heat pump water heater to direct the air over towards the wall. The ERV was a little bit noisy too, so I put a silencer in for that to make it a little bit quieter. So this is over the last 15 years or so. I ended up reducing the greenhouse gas emissions by 55%, the energy use by 75%, got rid of oil, and future plans, plan on doing a home edition hopefully this year, and another envelope retrofit, reduce the loads even more. Potentially solar PV, maybe geothermal preheat for the ERV. It runs through a defrost cycle, which makes it a little bit noisy, and so I'd like to take a look at that. Maybe eventually a new cold climate air source heat pump, and might make it to net zero. So a few lessons learned here. A few things. One thing was choose contractors that are familiar with their product. I know that whenever I installed the air source heat pump, the contractor had never installed the most efficient version of that heat pump before, so they ended up choosing the wrong indoor unit at first. They also didn't know how to wire it, so then I ended up rewiring it to meet the manual requirements. So I think it's important to make sure that's done, as well as monitoring the systems can help verify the performance. For example, the balance point of my heat pump ended up being better than expected, so it was great to be able to provide more heating and use the supplemental heat less often. Take into account noise with the equipment. I've had a few noise issues, and don't undersize your heat pump clothes dryer. And I think we need to push for a lot more of retrofits, at least this or even better, in a lot of other homes to really reduce carbon emissions across the province. That's it.